Let me introduce you. I'll just introduce you quickly.
Yeah, I'm Hurewicz, and today I'll be talking about the Borsuk Ulam Theorem, going over a pretty neat proof of it. I suppose before I do that, I should tell you what this is. I'm sure most of you know. So if you have a continuous map from Sn, and this essentially states that there's a pair of antipode points which map the same point. Well, if you just play around with it a bit, you'd notice that if you increase R by an extra dimension, if it's n+1, then this obviously doesn't hold true because you can just embed it. Like S1 would be just x squared plus y squared equal to 1 or something like that. You could embed it into Rn+1. And well, for the case n is equal to 1, it's a simple exercise of using the intermediate value theorem, where you just take the difference and then you do it. The general case here requires a bit of algebraic topology. So before I do that, I'd like to introduce two concepts. One of them is the degree. So if you have a map from Sn to Sn, and you take the homology, you'd be sending a generator to some value, say t times 1, because it's a mapping from z to z, and then that d is basically called the degree. And you could think of this as a generalization of the winding number, kind of. I guess it would be the degree thing if we had S1. That would make more sense. And another thing is homology of coefficients, which is pretty simple. You just replace the coefficients with something else instead of z. In particular, we're going to be dealing with z2. So this has the advantage that we ignore orientation because it's just there or it's not there. That's basically the meaning of z2. So before I go on, I just like to mention and write it down here, write a few facts which can be easily computed. One of them is, we have that h I of Sn in z2 coefficients is z2 for I less than n, and yeah, but it's 0 otherwise. And the same applies
you
for.
mean equal?
Oh yes, equal to. Yes, that is important. And the same applies for RPN. If you project the space.
So just n, not anything else for the sphere.
Oh yes. So sorry about that. Really sorry about that. Yeah, it's the case here. It's 0 obviously because there's only one answer. That's the case for RPN. And these facts will come useful when we move into the proof in general dimensions. So now that we have the proof for n is equal to 1, I guess using some basic covering space theory, we can tackle the proof of n is equal to 2. So that basically states that you have a map from S2 to R2, and we just assume that this doesn't hold true. So if you assume that this doesn't hold true, then you can construct another map, which is just defined take the difference and then you mod out, and this won't be 0. So
I got
this is the map from.
Sorry. You're a manager for PN. So you say that all the manager for PN is concentrated in degree 0 and n.
Less than or equal to all degrees.
Oh.
All degrees. If you're not working in Z2 coefficients, then you'd have zeros in between. I think in odd and even dimensions, you'd have 0, but we're working in Z2. So it would be Z2 everywhere.
Okay, yeah, okay.
That's
We're not understanding what you okay.
we can think of it. Okay, yeah.
Right.
Wait, did I not make it clear? Yeah, I think I should. Yeah. Okay, so now that we have this, we can see that this is an odd function. So we know that this holds true, and we can define a loop on S2, which is given by this, and we can just combine both of these two to get a new map, something like this. Now we have the usual. We can take a lift of this to get a map from the interval to R, and you can see with a few calculations that h s 1 by 2 is minus h of s, and that's because if you increase this by 1 by 2, if you just replace s by s plus 1 by 2, you'd get cosine of pi plus something, and then same for this. So basically, you switch sign, you get a negative sign there, and so that's why you get this. And using some more calculation, which I won't go through, but I'll just give like a geometric picture. So you have a circle, and then you have you have the thing. And if you have a pair of antipodal points, these are antipodal points, by the way. You can notice there's a minus sign. So these are antipodal points. If you have a pair of antipodal points and you lift them, you're gonna get something like, let's say you have this, and we lift it, take anything here, say here. We see that it differs by half and an integer. So you get an integer plus half when you lift it. So you should get that. In particular, we get that if you replace s by 0 and 1, this would imply that h of 1 is equal to 0 plus q, where q is odd. Now the reason we did all of this is, in our initial construction, we can see here that this loop is non-homotopic, and when you compose it, it'd be non-homotopic, but then this is odd. I mean, analytically, you can just take the cover, like something like E2 by IS, and then you can see that if you just put in odd things, it won't be non-homotopic. So you could think of it, you have the trivial loop, and then you have something which is non-trivial, and it can't be reduced to that. So that's a contradiction. That basically settles the proof for n is equal to 2. But n is equal to general n. I use some techniques, imaginary topology. So to do this, I prove something which is slightly stronger. So I prove that an odd map has odd degree. To see how this implies, Borsuk Ulam. Let's again we kind of do the same thing. We say that we assume that it doesn't, and we just construct a map here from S1 to Sn, which is defined as g of f of x upon norm of f of x, and you can have the inclusion of the equator, something like this. It's not really a circle. You get the inclusion of the equator. And we know that this is also odd. Yeah, we know that this is odd, and then we get that you have an odd thing here, you have an odd map, and if you take the homology by that theorem, which I'm going to prove, this would have to have odd degree of
G goes to Sn minus 1, right?
G goes. Oh yeah, sorry. That's Sn minus 1.
The last
then Sn minus 1 to Sn and Sn to Sn minus 1.
The other way. Sn to Sn minus 1 to Sn.
No, it's this way. We include it. It goes this way. The equator lies, so we include that, and then that one goes there.
Okay. Yeah.
Or yes. Okay, so wait, I think yes. I think you're right. Yeah. But then this would be 0 because it would have to. Sorry. This would have to factor through hn of Sn minus 1, and so it can't be odd. So to see how we can prove this, we can start off with the two-sheeted covering of RPN, and we can that's essentially just how RPN is constructed. You just take two antipolar points and then you match them. From this we get if you have an odd map from this odd map, we get a quotient map. And now I'd like to, and now we consider this, 2, and we define a map which takes these chains and sends them to their lifts. So you could think of this as you can think of it that way. Just to make it more clear. So we have this map here, and now we have the chains, coefficients in C2, and that's where it sends it to, through this map. So we get that. We have this map. And through this map, we get another map using the chain level to all of you can hear me, right? Okay. Now we have to prove that this is a short exact sequence that the image is of Z is contained in the kernel is slightly obvious because you just send it to the lifts and then you again map it through P. So if you go to you'd be sending that would go to 2 times of sigma, but then we're working in Z2, so that comes here. The other way can also work, but I'm just going to just leave that aside for now because yeah, I think you can just work that out. You can do that. This is an exact sequence, so I wrote yeah. Now we consider the maps induced in the chain level by this map and by this map. So you have okay, so we're going to be proving that this entire thing commutes, and the reason we're going to be doing that is so that we can construct we can get the long exact sequence and homology, and by naturality even that will commute. So this thing commutes, which sort of directly follows from the fact that by our usual construction this should be pretty easy to see. So once we know this, we just know this. However, for this we require just a little bit more work. So if you let's go through here. So we have this, and well, I don't insert coefficient because we're working in Z2, and we have this. And now, once we apply Z to this, we should get that this. And so now we're going to be sending these chains to the lifts, and again, I just leave the details aside, and you can show that these are exactly the. Now we go the other way, and we should get that. And from there, we just basically get the same thing. So now that we have all of this, we can basically move on to the the main diagram chasing part proof. So we this up. All of you can see it, right?
Make it bigger?
And larger. Yeah, all of you can just stop now. Okay. Yeah. So this is what we get. Now there's one thing to note here. It's that the maps are from Z2 to Z2. Oh, there are two things to note here. Everything which is not 0 is Z2, as I've presented right there. Everything which is not 0 is Z2. This is not 0 because, well, Sn has an n cell, and these zeros all come from the fact that, from this fact that it's 0 when it's not equal to n. so we get this long exact sequence. You have sort of pairs of RPN followed by zeros. Once you go in the middle, but at the end we know that that the homology does the nth homology or zeroth homology does exist. Yeah. So now the next thing to note is the homomorphisms from Z2 to Z2. This is obviously quite simple. There's just the trivial one, and then if it's not trivial, it's an isomorphism. So the thing to note is if it's injective or if it's surjective, that just means it's an isomorphism. So we assume that we have all the isomorphisms from HK, RPN, and also the isomorphisms induced by F bar star and F star. We have that for all k less than n, for both Sn and Sn. So the base case can be handled separately. So we know that let's say we have everything else. We have for all dimensions. We have that these are isomorphisms for all dimensions less than n. In particular, we know that we have that this is an isomorphism. That's by the induction hypothesis. By exactness, we know that that's surjective, which means that it's an isomorphism. Oh. Same applies to the left side. We know that that's an isomorphism. And using the exactness of this bar, we know that it would have to be the zero map because the kernel is zero, right there. So we know that this is the zero map, and in the same analysis applies to the bottom row. And we get that all of these three are isomorphisms. Since it commutes by naturality, we get that this is an isomorphism. But this is the same map as this, so this is an isomorphism, and we finally get the isomorphism that we needed. It is this isomorphism. So we get an isomorphism from so we get that F. Is an isomorphism. Both of these are Z2. So what that exactly means is that we have the degree of F, and we know that since it's an isomorphism, we know that has to be odd mod 2. I mean, it has to be 1 mod 2, which basically means it's odd. And then we're done. That basically proves the thing. But I guess a few interesting applications which can be done quite directly is the famous Rao fixed point theorem, and the ham sandwich theorem, which Rao fixed point theorem, the ham sandwich theorem basically states that if you have n objects in Euclidean space, then there's some lower dimensional hyperplane which divides them all into equal volume.